In this lesson, we're going to learn some ways to solve inequalities. Okay, so just to begin as a little warm-up here, let's think about some different possible values for some inequality statements, such as x is at most 12. So whatever x is, what are some different values it could be? Well, if it's at most 12, it could be 12. But it might be something less than 12, like 3 or 10 or 1, or -7 is less than 12. So x being at most 12 is some value of 12 or less. Here we have y is at least 50. Well, if it's at least 50, it means it could be 50, but it also could be a value greater than 50, like 51, 51.5, 100, and so on. So just to get your mind thinking about inequality statements there. So just to review, because you've definitely seen inequalities before, when you're graphing an inequality, an open circle and arrow is used for less than or greater than signs. So a less than and a greater than sign. And this is different than when we'll need to use closed circles, meaning filling in the circle, and those are used for when we have a less than or equal to or greater than or equal to. So always think about this, that the or equal to signs, you have to do more writing with the little line underneath, so they need more filling or more on their circles when you're graphing them. So just to review, if we have x is greater than 15, then let's put 15 on our number line. If x should be greater than that, this is strictly greater than, it's not or equal to. So what this means is that in the solution set of x is greater than 15, x actually cannot be equal to 15. So we leave it as an open circle and then draw an arrow to the right showing the greater than values of 15. So it could x could be 15.01. That is greater than 15, and anything to the right of that on the number line. Here we have a needs to be less than or equal to 7. So if I have 7 here, the or equal to means it can actually be 7. So we will fill in that circle to include 7 in the solution set, and all the numbers less than 7 are to the left on the number line. So to solve an inequality, we will use inverse operations and solve them just like equations. So when you're bringing something from one side of your inequality to the other, you'll do just as you would as if it were an equal sign. You undo the operations. There is one extra rule with inequalities, and that is that if you multiply or divide both sides by a negative number, when doing your inverse operations, then you must reverse the inequality symbol. So if it started out like this and you divide both sides by negative, you need to flip that sign to face the other way. So let's practice. Here we have the inequality negative 2x minus 7 is less than or equal to 5. We want to solve for x. So to solve for x, we need to isolate x, which means that we need to undo operations to bring anything that's being added or multiplied or subtracted or divided by x to the other side. So we'll start by adding 7 to both sides, which will leave us with negative 2x, keeping our sign the same, less than or equal to 12. 5 plus 7 is 12. From here, to isolate x further, we would need to divide both sides by negative 2. Right here, you are dividing both sides by a negative number. So this should indicate to you that you need to flip the way that your inequality sign is facing and now have it open to the x, or the left side. So then you get your solution to be x greater than or equal to negative 6. And if we plot what this looks like, then we have a closed circle on negative 6 because it is or equal to, and x should be greater than it, so that is an arrow to the right. And this means that x could be negative 5, it could be 0, it could be 10. Any number greater than or equal to negative 6 would make this inequality true. Here's another one to practice. So for starters here, to isolate x, we need to undo any subtraction or addition. So subtract 1 from both sides to get x divided by negative 4 greater than negative 2. Then, and we did not multiply or divide by a negative, so you keep your sign facing the same way. Then to isolate your x, you need to undo this divided by -4 and multiply both sides by -4. So here, -4 divided by -4, those cancel out and isolate the x for us. Now we did multiply both sides by a negative, so our sign will flip its direction and leave us with x less than a +8. -2 times -4 is +8. So graphing this on our number line, we have 8. Okay, and it's strictly less than, meaning it's not included. X must be less than 8. So 7.999 would be fine, but not 8. So we use an open circle. All right, here we've got x's on both sides. So just like with equations, you'll need to combine your x's and isolate them. So I'm going to start by bringing this 2x over to the left. It doesn't matter which way you go. You could bring the 4x over to the right, but I'm just going to subtract 2x from both sides, and that will leave us with 2x minus 2. 4x minus 2x is 2x, greater than 6. Now to isolate x further, we will add 2 to both sides, leaving us with 2x greater than 8. Divide both sides by 2. And there was no multiplying or dividing both sides by a negative, so our sign stayed opening to the left the whole way down, giving us x greater than 4. So if here's 4, x needs to be greater than it. Okay, so let's take a look at some compound inequalities, which are two inequalities with the word and or between them. An and statement means that both statements must be true to meet the parameters of the inequality. And the graph will look like an intersection of your two answers. So maybe this one graphed this way and this one graphed that way. So the intersection is their overlap. So those are the solutions that would make both inequalities true in that compound inequality. An or statement is when only one of the solutions that you find has to be met to make the inequality true. So in an or compound inequality, you might have this one graphing this way, this one going the other direction, and as long as you have either a value that makes this portion of the graph true or a value that makes this portion of the graph true, then it will make your whole inequality true. It's an either or scenario. So with compound inequalities, to solve them, you will start by separating your problem into two inequalities. Then you will solve for each problem separately using all your normal rules and graph each answer on a single number line. They do graph onto the same number line, and the combined graph and inequality will be your final answer. So here's a compound inequality. And so we've got 3 less than or equal to 2x minus 3 less than 15. This is an example of an and inequality. So to break it apart and solve, you will break this into two separate inequalities. So what I do is I always think about the middle part overlapping. So the first one is made up of 3 less than or equal to 2x minus 3. The second inequality you can write is made up of 2x minus 3 less than 15. So breaking those two equations apart, you'll notice that 2x minus 3 is in both inequalities that you set up. The middle piece goes in both fully. Now from here, you'll solve each of these separately. I'm going to give you a moment to solve for x here on the left and solve for x here on the right. So click pause, and when you're ready to check, click play. Okay, so isolating the x's on the left side, you should have added 3 to both sides, then divided by 2 here, add 3 to both sides, divide by 2. So we get that 3 is less than or equal to x, and x is less than 9 as the two possible solution ranges here. So to combine your answer, you can write this either as, if I can rearrange this order anytime as long as I keep this facing the x or opening the x. So you could write this as x greater than 3 and x less than 9. However, if you're not sure if it was an and or an or scenario, we can always write our final answers using just one x. So what we'll do is put that x in the middle one time, And then just make sure it's opening the right way to the 9 and to the 3. So here it opened towards the x, not the 3. So I kept that sign exactly the same, and here this sign the same. And this is an acceptable way to write this solution. Now to graph something like this, I prefer to see my variable first. So I would rewrite that 3 less than or equal to x as x greater than or equal to 3. They are the same expression. I've just written it with the x first. So I do like to see that because to me that makes it easier to tell which way my arrow's going. So if x is greater than or equal to 3, that one goes to the right. And if x needs to be less than 9, that's an open circle here, going to the left. So you would shade this overlap region, and this represents the solutions to this compound inequality up here. Any number that falls either on 3 and all the way up to 9, but not including 9, would make this inequality true. And you could try it. You could put 5 in. You could put 4.7 in for x, and it should make both sides true. Here's an example of an OR, compound inequality. We have the word OR to separate them. And this is really, just think of it as two separate inequality problems to solve, and at the end you just graph them on the same line. So go ahead, solve each of these for h, get your two ranges for your h values, and then we'll check together. So click pause. When you're ready to check, click play. Okay, so we added 10 to both sides on the left, subtracted 3 from both sides on the right to get h to be less than -4, h greater than or equal to -1. So you can write it like this, or you can still write this as -4, -1. All combined in one. So if h is less than -4, it is opening towards the -4, so I keep it opening towards the -4. And here it's opening towards the h. So this is also an acceptable way to write your solution. So we have h needs to be less than -4, and h needs to be greater than or equal to -1. So here is confirming that it is an OR. You can see there's no overlap. It's, you know, x could be -7 or it could be 3. Anything that meets the solutions, these two arrow portions would work. The region of values that would not make this true would actually be in here. So these are not solutions in there. And that concludes our lesson on inequalities.